The 21st century is an exciting time to be alive, especially if you enjoy space and space travel. It is very likely that by the end of the century, there will be human cities on both Mars and the Moon, and the technology to make this happen is already being developed or it already exists. It is now time to make a pretty major decision. Which of our two closest celestial bodies do we attempt to inhabit first? But before we really get into that, I want to address a pretty common question, which is why should we go to either when we have all these problems back here on Earth? It's a question that's been asked pretty consistently since space travel was first being tested in the 1940s and 50s, and the answer is actually within economics. In economics, standard of living increases when technology advances to the point where products are cheaper without lowering their quality. The most common way this takes form is the acquisition of cheaper materials. The first industry that would see cheaper materials from the moon would probably be the electronics industry. The moon has copious amounts of metals like gold hidden in the dense material left by asteroids impacting its surface, something that many electronics use and something that is also very rare and expensive here on Earth. On Earth, there is a set of three basic needs all humans need to survive, those being food, water, and shelter. On any other celestial body, the list includes these three plus two more to make five, those being oxygen and compression. In order to determine which body would be the best to attempt to live on, it would be easiest to compare the difficulty, abundance, and cost of acquiring each of these needs. The basic need that quite possibly plays the largest role in this selection would probably be liquid water. The most efficient existing cargo rocket is currently SpaceX's Cargo Dragon launched from a Falcon Heavy. If fully loaded, the cost of delivering water to the ISS is still roughly $9,100 per pound. Now, knowing that the average human consumes about 2 liters of water per day and knowing the density of water, that comes out to about 4.41 pounds of water per day, which would cost about $40,000 per day. That's a lot. But the ISS has a system known as the Environmental Control and Life Support System, or the ECLSS. I'll just call it the ECL for time's sake. The ECL recycles water at great efficiency, about 90% actually. This would reduce the cost per day of sending water to about $4,000 per person per day. This is just to send water to the ISS, which is in low Earth orbit. Sending water to the moon and to Mars is a much greater task and will be far more expensive. It is completely infeasible to send a constant supply of water to an extraterrestrial outpost. So the question then becomes, what are the options for creating water on site? Creating water on Mars is, theoretically, very easy actually. A great deal of the Martian surface has a thin layer of ice directly below the dusty surface. Creating drinkable water would be as easy as melting this ice and filtering it using either a solid filter or reverse electrolysis. Reverse electrolysis is just a fancy way of saying splitting it into its hydrogen and oxygen atoms and then combining them back into liquid water. A solid filter would be a cheaper option in the short run, but would technically require a semi-constant flow of clean filters to the outpost. Reverse electrolysis only requires the initial shipment of the equipment and electricity to run said equipment. Which option is more cost efficient would require a very detailed analysis using factors that we really don't know yet. The main point is that both options are decently cheap, simple, and with ice over most of Mars's surface, water would be in abundance. The moon, however, is a bit of a different story. The moon has been pelted with asteroids containing various elements since its formation 4.5 billion years ago. Thanks to this fact, the lunar regolith, the dusty material that sits on the surface, contains actually a good deal of oxygen. This oxygen exists in a solid form bonded with other elements in many compounds like fluorapatite. Over time, hydrogen jettisoned from the sun's corona, or outer atmosphere, bonds with the oxygen in these compounds and forms what's called a hydroxyl group. Most any element oxygen bonds with creates an exothermic reaction, meaning it releases energy. So in order to reverse this process, all that's needed is to add energy, mainly in the form of heat. Although, unlike melting ice, this will require quite a bit more energy. The hydroxyl HO- has a negative charge and will look to bond with a hydrogen atom to form H2O, or water. This process, though, is untested, so it is hard to pinpoint an exact cost. The previous method for water production on Mars is also untested, but is simple enough that it is very unlikely that any step of the process would not work as described. Now, the European Space Agency, or the ESA, is currently funding and working on a project to extract water from lunar regolith, but it is unclear how effective the process will be currently. With too much unknown about water production on the Moon, Mars starts with an early lead in the most important category. It's important to note, however, that water production on the Moon is a problem that NASA's Artemis program aims to solve soon. Moving on from water, it is very easy to get a good idea of how oxygen generation will work on either celestial body. Oddly enough, the process of creating oxygen is theoretically much simpler on the Moon than it is on Mars. Using the water generated on the Moon, the process of electrolysis can be used to split water into its components of one oxygen atom and two hydrogen atoms. The oxygen atom can be released in the air to replenish what is lost, and carbon dioxide can be removed with a very simple carbon dioxide filter like those used on the ISS made of zeolite. An added bonus to this is that the leftover hydrogen can be reintroduced into the process by using it to combine with hydroxyl as described in the process for creating water, making a closed loop and self-sustaining. This is quite convenient, but a major downside is that it taps into an already dodgy water production cycle that is, again, untested. Interestingly enough, the prevailing method for oxygen generation on Mars has been tested. On the Mars Perseverance rover that launched on July 30th of 2020, there was a small technology demonstration system known as Mars Oxygen En-Site Resource Utilization Experiment, or MOXIE for short. MOXIE uses the Martian atmosphere, which is about 96% carbon dioxide, to produce oxygen using nothing but electricity. While the system is tested and it's found to work, it's a bit slow, and a large enough model to produce the required amount of oxygen for a Mars mission would likely be around 100 times larger than the current one on Mars, which is about 1 cubic foot, making a full-scale model large and heavy. The cost to implement both of these systems isn't something that can be said for sure yet, but both systems seem promising in theory, so we can call this category a tie, which leaves us with Mars still in the lead. The next basic need is shelter. While on Earth, not having shelter can be summed up as being exposed to the elements. This typically includes dangers such as storms, extreme cold, extreme heat, etc. In space, however, this means being subjected to the sun's deadly rays. Without a thick atmosphere and ionosphere to protect them, Mars and the Moon are under constant bombardment by lethal doses of solar radiation that will easily kill any unprotected life. That being said, the story of what a shelter needs to provide changes quite a bit. Any system, whether it be on Mars or on the Moon, would most likely consist of two elements. The first element being the actual habitat that the astronauts live and work in, and the second being some sort of crude structure that protects the first element from the sun. A question that might form in your head very quickly is, well, why can't the first element protect the astronauts from the sun's radiation? And this question has two answers. The first answer is the fact that radiation and thermal shielding is very heavy and very impractical to have to transport to each body. The second answer is quite a game changer though, and that's that the second element already exists on both bodies in the form of caves. While Mars has caves carved out by erosion from when liquid water flowed on its surface a very long time ago, the Moon has caves in the form of lava tubes that formed when the Moon was young. Even if the option of caves does not work out for either body because a better site is selected for any other reason, there is quite an easy solution, and that's just, well, bury the base. The surfaces of both bodies are composed of dusty material that's quite easy to move around. The habitats of the base can simply be covered with a decently thick layer of this dust to keep it safe. This will also provide more insulation. Which option is best and cheaper is yet to be seen, but both options are well within the realm of possibility, so again, a tie is made in this category, but again, Mars is in the lead. That's 3 of the 5 needs down. All that's left is food and compression. Food is the more difficult need of the two by quite a long shot. Human nutrition is a very complicated science, and any astronaut attempting to live on another planet needs to have a healthy diet. Thankfully, testing on crop growth has already taken place. On the ISS and on Earth, tests regarding specific crop growth in low light and low gravity environments have been quite fruitful. A test regarding growth of Chlorella vulgaris was especially promising. Chlorella vulgaris is a type of microalgae, and from here on out, I'm just going to call it the algae because I'm going to butcher its name every time if I don't. Now, the algae on Earth serves as a protein substitute. High in protein and capable of growing rapidly in low light environments, such as those made with artificial light, the algae is a perfect example of a food that can be grown on either body, not consuming much water, producing lots of oxygen, and unaffected by the low gravity due to it being a group of unicellular organisms. Of course, an astronaut cannot fully sustain themselves on nothing but algae for months on end, no matter how nutritious it is. That has too much of a psychological impact. In the early days of a colony, a good morale would be a very important aspect. Studies done by NASA show that food can have a great effect on morale based on whether the crew members enjoy what they're eating or not. So other foods would need to be produced to help keep a diverse diet and attempt to have the crew not burn out on a particular food. On top of nutritious crops, spices would also be grown, most likely, to keep food interesting, or to keep algae, palatable. Most foods like this will be grown using hydroponics, or the growth of crops without the need for soil. Hydroponics also notes a not insignificant decrease in water consumption of crops. Much like oxygen generation and shelter, there isn't a clear winner here since the same system would probably be used on both bodies. The last of the needs is compression. This is also the simplest to solve. In fact, a solution has already been developed. On Earth, humans are subjected to about 14.7 pounds per square inch of pressure from the 300 miles of thick atmosphere above sea level. Now, this number may seem astronomical, but it's important to note that the most of the atmosphere lies within the troposphere, or the first 10 kilometers above the Earth's surface. All of that pressure helps keep our body together, but on other celestial bodies where there may be little or no atmospheric pressure, human tissue will expand, causing stiffness and joint pain that will only get worse the more exposure to low pressure. While in the habitat, this won't matter since the air provided to the habitat will be at pressure and the human body won't decompress. But in order to have a thriving colony, most work will be performed outside in the elements. Compression wouldn't be an issue if workers could simply work in the pressure suits like those used on spacewalks and the ones used on the moon. But these suits are very limiting when it comes to locomotion or movement. A suit that provides the perfect movement while being pressurized does not yet exist and most likely never will. The best solution to this problem is to have the astronaut wear a thick suit that protects them from the elements while only having a pressurized helmet. In order to deal with this problem, a suit is being developed that would remain skin tight, giving the user full range of motion while using mechanical pressurization, or just being really tight, to keep the astronaut at the 1/3 atmosphere required to keep them from decompressing. Much like the previous needs, there is no clear winner here since the same system is implemented on both planets. If the analysis were to end here, Mars would be the clear winner, but there are still 2 very important topics left to cover. The first of the topics left to cover is also, quite possibly, the greatest counter-argument to colonizing the moon, and that's the terraformation of Mars. Terraformation is the process by which a planet that was once impossible or difficult to inhabit becomes an Earth-like planet with sufficient resources to keep humans alive without the need for special equipment. Basically, changing a planet to resemble Earth. Within reason, it is possible to terraform Mars. This is because of many reasons, including the fact that Mars has enough gravity to keep an atmosphere thick enough to insulate the planet, already has water on its surface, and its ability to keep radiation and solar wind away with an ionosphere. The moon, on the other hand, would be very impractical to impossible to terraform due to its lack of resources needed and the insufficient gravity to hold a thick atmosphere. So many ask, if we can never make the moon livable without special equipment, why even bother touching it? The short and simple answer is because of all the rare resources on the moon that we can harvest. Another answer, though, is the sad fact that the terraformation of Mars would most likely take hundreds, if not thousands, of years to complete. The resources to terraform the planet do not exist on the planet itself. Certain materials, like water, would have to be shipped in massive quantities to the planet from other celestial bodies, like Jupiter's moon Europa. Another major resource that Mars is missing is nitrogen. Nitrogen is an element that is used in many organic compounds, and it is mostly used by plants to grow in soil. In hindsight, terraformation shouldn't even be considered when deciding where to make a permanent colony today. The cost of terraforming Mars will be so exorbitant that humanity most likely won't start the process in the 21st century. This entire time I've been walking and walking, and I'm finally about to reach my destination, the moon. No, not actually, but I've walked about a mile. And let's say that that mile is comparable to the maximum distance that the moon and the earth will ever be away from each other. Now, using this same scale of measurement, then the distance from Earth to Mars would be about the distance from Kansas City to Hawaii. Yeah, it's quite a bit further away. The distance from the Earth to the moon doesn't really change all too much. It does change, but relatively speaking, it does not change that much. The distance from Earth and Mars, though, change quite drastically. Since Mars and the Earth both orbit around the Sun at different heights, to get to the red planet, a Hohmann transfer trajectory is used. A Hohmann transfer trajectory, or just an HTT, is a space flight plan that allows for an absolute minimum fuel to be spent. It is also important to note that it is never the case that this trajectory is also the shortest. While everything stated so far has been facts and quantitative data, the conclusion is still an opinion. And it's the opinion of people like Elon Musk that they want to go straight for Mars. Yet the fact remains that an organization like NASA should try to look past opinions and decide the best course of action based on quantitative data. The current NASA Artemis program has its ultimate goal to research possible human landings on Mars, while it should be the first step for humans to have permanent habitats on the surface of the moon. Hey there. On screen now should be a list of sources I used to create the paper that this video is based off of. Something that is very important to note is that I am by no means an expert in this field, and this is amateur research. So any facts said in this video could straight up be wrong, or my opinions and conclusions could be inaccurate to the research I presented. Who knows? This was just a project I enjoyed making and wanted to put out there. So thank you for watching if you made it this far.